Good Friday morning, Backyard Naturalist community. My name is Tim, and I will be your host for this edition of the Urban Ecology Center's Backyard Naturalist. It's October, and when October rolls around, the Backyard Naturalists start to get a little bit creepier, a little bit scarier, a little bit spookier. Not as scary as the Brewers playoff loss, which I have to admit has really put me in a funk. But we'll get over it. There'll always be next year. This is what being a Brewers fan is. It's the heartache this time of year. It's become a traditional sign of fall. My beloved crew, first round playoff lost. Uh, but this is the Backyard Naturalist, and today we are featuring a landform, sort of, one of the scarier landforms, which is why it's in October. It's kind of a landform, question mark. It's kind of a water form, kind of sand, and a quicksand. Why is it quick? Quicksand makes a great movie and TV character. It helps build suspense, it helps build intrigue and danger. You have to be careful where you step. And this is this is for those of you at least that grew up in my generation and previous. Gilligan's Island is pretty much the show that I think of. But for the newer generation, there's The Simpsons, Blazing Saddles, of course. And one of the characters in Blazing Saddles describes what's happening. That he says, "What is it that ain't exactly water and it ain't exactly earth?" And I think that really sums up quicksand, both from a scientific perspective and the media perspective. So it's not exactly water you would swim in, and it's not exactly earth you would walk on. And so we're going to look at that today. Is it really dangerous? Is it accurately portrayed in the media? Is this something we should be concerned about? And those are the stories we're going to explore today on episode IV of season VI of the Backyard Naturalist, which is the quicksand and the dead. And speaking of media, with a nod to PBS, we are honored to thank the viewers like you who are here with us this morning live, as well as the viewers who are here with us at a different time watching the YouTube video. Thank you. I'm glad you're here and I'm honored to share this time with you. If you enjoy this episode, I encourage you to look into the benefits of becoming a subscriber. If you have the means and the desire, your subscription really helps keep this program sustainable into its sixth season. It's VI season. There are both seasonal and annual subscriptions, and we are about to start the benefits of the new super subscription, which is a new field trip series that we're calling Green Spaces and Familiar Faces. The first one starts next week, and they'll be about once a month. We'll be exploring some of the favorite green spaces of local naturalists. It's kind of like a show and tell or a book club, but instead of someone sharing their favorite object or book with a group, they'll be sharing their favorite local green space with us. And I'm super excited to be part of this new effort. And for more information, you can visit the Urban Ecology Center website or talk to a member of the UEC's research team. The first familiar face will be local legend Bill Miller, and I will be sending a message to super subscribers today. The first one's going to be a week from Saturday with Bill Miller, and the entire season lineup is should be ready in the next week or two. We got some great folks lined up. I'm also excited to announce the next Urban Ecology Center course that is brought to you by the research team, which will be a winter ecology course that will take place on Wednesday evenings in February. It'll be part classroom, part outside learning experience, kind of college level, but without the college pressure. We live in a part of the world where temperature swings quite drastically throughout the year. And for a few months at least, it can get, we hope it gets really cold. So cold that the water freezes, the precipitation freezes and forms a layer of snow. And then the wildlife and plants in our area have adapted to those seasonal changes, and we'll explore those adaptations. And of course, since this class is being offered by the Urban Ecology Center, we will focus a little more on the urban plants and wildlife we find in places like Milwaukee in the winter. And the course will be one of the first ever programs from the newly renovated Urban Ecology Center at Washington Park. If you haven't driven by the park recently and seen the building, it looks pretty cool. So you can be a part of history. Put this date on your calendar. Saturday, February 1st is the grand reopening of the building, and it will also be Winterfest. So February is a great time to celebrate winter, and the Urban Ecology Center is offering several ways to do just that. So we hope you can join us for Winterfest and the grand reopening, and for the winter ecology course that will start a few days later. Because it is October, I'm excited for the scary, not so scary topics that are coming your way. In addition to Quicksand, we've got some very special guests, including UW Green Bay spider expert Michael Draney and former UEC community scientist and PhD candidate at Penn State, Will Voigt, who recently was featured on PBS. And they will bring you backyard naturalists on spiders and snakes, respectively, the vilified and often misunderstood and underappreciated and regular guests to this program, and to many very scary and spooky elements of our backyards, as well as a program on maybe the scariest Halloween organism of them all, which is sugarcane. So we can look forward to some really fun shows for the month of October. If any of you have been to the Galapagos on your own or with the UEC, you'll probably recognize the tortoiseshell that Will is perched in over here. And before we get started on Quicksand, when I host the Backyard Naturalist, I do like to pay attention to what's going on in space, because space is connected, at least visually and in other ways, to our backyards. We've been following a few exciting recent space missions that are now either over or on pause, but there are a couple new missions about to play out in October. So we're starting with the European Space Agency's Hera mission, and this is a planetary defense mission. So not planetary like Space Force, like weapons in space to protect us from other countries. This is more the planet-wide protection from things beyond our planet, asteroids mainly, that could cause catastrophic events here. So this is coming on the heels of the recent mission from NASA, which was the DART mission that we followed here. And that studied the possibility of, can we deflect an Earthbound asteroid that could destroy us? And so that was the mission where we rammed a spacecraft into the asteroid Dimorphos to see if we could affect its orbit around its binary partner, which is Didymus. And it was successful. It slowed down the orbit by roughly a half hour. So Hera, the mission that's about to launch on Monday, is hitching a ride with two other aircraft, of course, on the SpaceX Falcon 9 rocket. And this will be a 2-year journey to that same binary asteroid system. And part of the mission is to study the after effects, the impacts of that first mission by DART, and also to get a better understanding of these two binary asteroids, because pretty sure these are going to be the two that we're really going to focus on as we continue to look for ways to see if we can affect objects that could cause a danger to Earth. So that is going to be launching on Monday, hopefully. And then a few days later, NASA's going to is set to at least launch the largest spacecraft it has ever sent to another planet. It's the 10-foot-long Europa Clipper, which is on its way to several of Jupiter's moons, but mainly Europa. And it is really, hopefully, going to investigate the potential habitability of that moon, mainly to other life. So it's not going to be investigating if there's life there. It's going to investigate the conditions to see if it could support life. And of course, they're also using SpaceX. They're kind of securing, feels like a little kid in their basement with toy rockets, but they're basically putting 3 SpaceX Falcon rockets, strapping them together to provide the fuel and force to get this thing in. So they're getting rid of anything that could be used. A lot of SpaceX rockets are designed so that they can leave and then come back, but they're getting rid of they're not any hope of getting these rockets back. They're basically taking the essential parts, putting 3 rockets together, because this is a big, heavy object, and then it's gonna launch, hopefully. And it's got a little bit of a interesting way to get to Jupiter. It's first going to go to Mars, and then spacecraft will often use planets to use a gravity-assisted speed up kind of like slingshotting through its atmosphere. So it's going to go to Mars, and then it's going to build up speed and then come back to Earth. And then the Earth is going to do another slingshot, and then it's going to head to Jupiter, and then it's going to use one of the other moons of Jupiter, Ganymede, to slow its velocity before mainly a 4-year mission to study Europa. It's also going to study some of the other moons. And it's going to analyze the thickness of the moon's icy crust and ocean interior. These are things we've already found. And then whether there are pockets of liquid water within that ice. So it's really investigating the composition of the ocean, the crust, and the atmosphere, and determining a bunch of things, among other things, how salty the ocean is, whether liquid is working its way from the surface to the surface and from the surface. Basically, a big old textbook geological study of the landforms that are there, past and present activity, and of course, to see whether life could exist within the ocean. And there is another field of study that's looking at life, but not the carbon-based life that we know of. It's looking for non-carbon-based life form, which could be on Earth in areas that we just haven't figured it out yet, that have the properties of life, but just not the narrow definition that we determine as life. So really interesting. Again, it just feels like a big ol', they're making the geology textbook from Earth, but now they're making the geology textbook for Europa. So super interesting. I'm really excited to see what happens there. And then for those of us planted here on terra firma and not sinking into quicksand, we can look forward to trekking Comet over the next month. There's for the month of October, Comet Chu, I'm going to butcher this pronunciation, Chuchinshan Atlas, that's easier to say, is going to come within 44 million miles of Earth. After and if it successfully orbits around the sun, there is a chance the sun will destroy it. But if it survives the close encounter with the sun, the scientists are expecting an impressive sight. It is possible to see it already in the morning skies, and it has already passed the sun, so it's looking good. And it's going to become much brighter. It's currently a morning object. It's going to become an evening object over the next few weeks. And astronomers expect that this could be one of the brightest comets we can see and have seen from Earth. So likely easy to see with the naked eye, but I learned comet brightness, like the weather, can be notoriously hard to predict. So a professor, Kwanzi Ye, a planetary astronomer at the University of Maryland, had a good quote. He said, comets are like cats. They have tails. They do what they want. So almost for every case, it's not going to end the way that you predicted, and we won't know until we get there or it gets here. But with each passing day, we should know more, and we can hope that this will be one of the brighter comets that we see in our lifetime. And as the comet goes away, we will be greeted by one of the better known meteor shower, the Orionids, which peaks the evening of October 20th, is visible now, or we should be able to see meteors now. And the morning of the 21st, that's going to be the peak, active from now through early November, November 7th. And it's known for bright, speedy streaks emanating from Orion's belt as the Earth passes through debris from Halley's Comet. It's the partner meteor shower to the Eta Aquariid meteors, which peak in May, which is also part of Halley's Comet. So we're kind of going through both parts of Halley's Comet tail. And unfortunately, the peak comes a few days after a full moon. So not ideal conditions, but still should be a good show over the coming weeks. So the spooky topic we're here to talk about today is quicksand. And I need to give my regular reference to one of my favorite sources of information for Backyard Naturalist, Stuff You Should Know, How Stuff Works, that compendium of articles, videos, podcasts, and a wealth of really fun information about stuff you should know. So quicksand was a really interesting topic to explore because there's so many levels of understanding of what quicksand is. It's not easy to define and it's not easy to understand how it works, what we may want to know for our own safety. In part, we're exploring a part of a form that happens in several ecological communities. So it's again kind of a landform, kind of a wetland, kind of a coastal landform. What we call quicksand can be found in a variety of habitats. We're also exploring the physics of quicksand, and we're diving into, pun intended, a field that looks at the characteristics of matter flow, and particularly unusual matter like quicksand. So there are a lot of sciencey ways to look at quicksand, and then of course there's the media portrayal and what was ingrained in us, mostly as kids, mostly in Gilligan's Island. So again, I think we're limiting ourselves to people born probably in the 70s and earlier, although it has stuck around in some very popular movies and shows that the younger generations will know as well. So let's start with quicksand from a sciencey perspective. Technically, quicksand is a colloid, meaning it's a mixture of two substances, one of which is insoluble particles that are suspended and dispersed in another substance, which is most often a liquid. So a solid dispersed and suspended in a liquid, that's what makes it a colloid. In the case of quicksand, you have solid particles of earth that's in granular form. So that could be sand, it could be silt, it could be clay, and almost always it's dispersed and suspended in water. So we're not just talking about wet soil, we're talking about what should be or wants to be or was solid ground that becomes supersaturated or liquefied. Now, sand is a big part of this, and to call sand solid ground is a little bit of a stretch to begin with, but sand is pretty movie. But that's really what we're talking about. Again, it could be sand, it could be dirt, it could be a lot of things. And so these are the building blocks of quicksand, some form of earth that is suspended in water and not separated. What turns the suspension into quicksand is usually a consistent presence of water or a disturbance. And so there's, again, quicksand can be used to describe quite a lot, quite a variety of forms. And we'll look at maybe the most common ways that Earth becomes quicksand. So one of the most common conditions for forming quicksand is when you have either standing water or the upward movement of water without an outlet. So probably the basic standard would be an artesian spring bubbling up to the surface. That can be in a lot of different areas, including beaches. And what it does is it supersaturates the soil. So the soil is now suspended in water. And sometimes, again, sometimes the water is just staying there. But sometimes that upward movement of water from a spring kind of keeps the area in a quicksand like environment because it's acting opposite of gravity and it keeps the soil in that permanent state of suspension. It keeps it from settling out and separating from the water. So that's in a nutshell what forms one of the most common ways to form quicksand, and it can be again in a lot of different environments. So they can be in grassy environments, often near wetlands and bogs or flooded savannas. They can be a little more movie-like, and you can find them in wet forest environments. Um, Not usually caused by seasonal flooding, but areas where there is flooding can happen. And again, it can also happen where groundwater comes to the surface. It can be near lagoons. It can be near mangroves, but this could be well inland. It doesn't have to be near the coast. One of the common places for quicksand that we learned firsthand from Sunny before this started is in beach environments, where you have stretches of sand And can be particularly bad if you have an upwelling spring like you see here. Or it can just form right on the beach, especially if you have a wide, flat beach, because it's close to sea level. The high water table mucks up the sand and causes it to be suspended. And it is stable until you disturb it. And that can be your foot. And as Sunny mentioned, sometimes it just doesn't look any different from the sand that you're standing on. A lot of these slides show the water, but a lot of times you don't see that water. And they can occur in tidal areas. They can occur in non-tidal areas. That's important consideration for later. They can be in deserts. They can be in forests. They can be just about anywhere, but much more likely to be where you have the groundwater close to the surface. And quicksand can form along low, flat riparian areas of bigger rivers. So this is the Thames River in England. And that's kind of the majority of the types of earthquake or quicksand that we find in the environment. The other common way of creating quicksand is the more catastrophic earthquake quicksand, and that's a slightly different process. This is a little bit more going into like how sinkholes form, but basically what happens is the earthquake loosens the particles of soil or sand and simultaneously introduces water, and that's a process called liquefaction. And so essentially, this is the instant the ground pretty much turns into mush and it can swallow cars, can swallow you, can swallow buildings. So that's the other more extreme and real type of quicksand. So wherever the quicksand is, the trapped or upward flow of water is kind of forming a liquefied cushion of sediments that gives the quicksand a spongy, fluid-like state. So again, part water, not exactly land, not exactly water. And if you introduce an object into quicksand, whether it be a human body or a bowling ball, the object will sink to the level where the weight of the object is equal to the weight of the displaced quicksand. And this is mainly determined not just by weight, but by density or the relationship between an object's mass and its volume. So first, we need to look at the density of quicksand. And there are different kinds of quicksand, but on average, quicksand is about 2 grams per mil. That's the measure of its density. 2 grams of mass for every milliliter or cubic centimeter. So if you were to scoop out a milliliter of quicksand, it will weigh about 2 grams. So this starts to mean something when you compare it to other objects. To simplify it a bit, objects that are less dense than 2 grams per milliliter should float in quicksand. Objects that are greater than 2 grams per milliliter should sink to the point where an equal amount of mass has been displaced. And another important reference point here is water. So water is roughly 1 gram per milliliter, and this can change with temperature and dissolved salts. You know, the the salty ocean has a different density than fresh water. And so, but for the sake of argument, we're going to call water at a, roughly 1 gram per mil. So water is about half as dense as quicksand. So this should allow us to predict what objects would sink or float in both water and quicksand if you know the density of the object. And again, in theory, there's more things at stake here. So being in Milwaukee, let's start with a bowling ball. And we know that a bowling ball isn't just a bowling ball. So we'll start with an 8-pound bowling ball. An 8-pound bowling ball has a density of 0.92 grams per milliliter. So it is less dense than both water and quicksand, meaning if you drop an 8-pound bowling ball onto quicksand or into a lake, it should float. So lighter bowling ball is going to float no matter where. If you plop it into a, quicksand, plop it into a bathtub, it should float. There are, of course, heavier bowling balls. So a 16-pound bowling ball has a density of 1.33 grams per mil, and that makes it more dense than water, denser than water, and less dense than quicksand. So if you drop a 16-pound bowling ball in a lake, it will sink. But if you drop a 16-pound bowling ball onto quicksand, it will float. And I don't mean like float on top of it. Of course, it's going to have mass, and depending on how you drop it, it's gonna lodge into it, but it's not going to sink. So you don't have to worry about losing your bowling ball to quicksand no matter how heavy it is. But depending on what type of bowling ball you have, you could worry about losing it to a lake or river because some bowling balls float and some bowling balls sink. An important thing to know here in Milwaukee. So let's look at another object. Let's look at steel. Steel is one of the densest materials we know about. It has a density of almost 8 grams per mil, 8 times the density of water, 4 times the density of quicksand. So steel is going to sink in water, it's going to sink in quicksand, and I featured steel because, again, we're in Milwaukee, and from a historical perspective, when Byron Kilburn tried to lay the first steel railroad lines in the Menominee Valley, close to where the current Amtrak station is, in the wetlands. It wasn't even quicksand, it was wetlands. They laid the tracks, came back the next day, and the according to Gerda, they found that the tracks had sunk about 8 feet into the wetlands. So even mostly solid ground in a wetland can swallow something up as dense as steel. If you're that dense, you don't quicksand or not, you have to watch where you're walking. Fortunately, we are not as dense as steel. So it can't swallow a bowling ball. It can swallow steel, and what we really want to know is, can it swallow up a human body? So from a physics standpoint, the question is, what is the density of the average human body? Will it float or will it sink? And it turns out the average human body is about 1 grams per mil. We are about the same density as water. So it's relatively easy for us to float, depending on your body, of course. Some of us float more easily than others, but because we're about the same density of water, it is fairly easy for us to swim and float in water. If the water is salty, it makes us float more easily because it increases the density of the water. But we're kind of right at that border. Some of us will sink faster, some of us will float, which means from a sciencey technical perspective, it is almost impossible for us to sink in quicksand. So I hope I'm not bursting your media bubble, but the media did lie to us. And science backs this up according to a 2005 study published in the journal Nature by Roxanne Comsey. We are just not dense enough to sink into quicksand. Now, this doesn't mean quicksand can't be dangerous to us, as we heard from Sunny's story this morning. Remember, quicksand caused by earthquakes can swallow us up, no matter how dense we are. It can swallow up a car, it can swallow up a building. So in that catastrophic kind of quicksand, yes, it's dangerous. But what it does mean is that you're not going to drown in it in that slow manner like you see in the movies. So I love this. The Nature Journal mentions a scientist from the University of Amsterdam, Daniel Bahn, who recreated artificial quicksand in the lab that had the same properties as quicksand they collected from the wild. And they tried their best to sink objects that had the same density as humans. And, you know, poor little Tasmanian devil, or actually fortunate Tasmanian devil here, they could not get it to sink into quicksand. They could push it down, they could drop it and get it to get stuck more deeply, but they couldn't get it to sink. And the reality is a lot of quicksand isn't that deep. So like if you see this kind of quicksand is on a flat table, there'd be a point where the devil or the human actually could hit the bottom. It's not always the case, but a lot of the cases, and from some of the stories that people tell about being stuck in quicksand, some of the commonalities is you're panicking, you're sinking, but then you realize, oh, actually, I can just stand up, right? Similar to water, if you're swimming in water and you realize you can stand on the bottom. So that's that's one of the reasons why that Hollywood system doesn't occur very much. But there are properties that make quicksand dangerous, and we can absolutely get stuck in quicksand because of our mass and shape and gravity. So even though we won't sink, we can easily get stuck. We can easily get a foot or part of a leg or deeper. Any of us that have ever stepped into mud even and pulled your foot out only to see your boot swallowed up by the mud, your foot comes out, but your boot doesn't. We know that it can be hard to pull out. It can be really hard to pull your foot out of quicksand or mud. Because what happens is that before you step into quicksand, the sand or mud particles are supported by the water, and your foot is adding a disturbance. The sand loses its stability and actually starts to flow downward quickly, rapidly. If you're putting pressure on it from above, that solid suddenly behaves like a liquid and sinks. So this is similar to what might happen to a neatly stacked arrangement of fruit. Right now they're stable, but if you add a disturbance, the fruit is going to start to act like a liquid and pull downward by gravity. And that downward pull, if it's sand or clay or dirt, will swallow your foot. And oftentimes the ground looks solid, but you're stepping on it, again, liquefies it in a sense. So the water and sand separate, and that leaves a layer of very densely packed wet sand. It becomes more like a solid after it's a liquid, and that's what traps your foot. The friction between the sand particles themselves is much reduced. So at first it can't support your weight, but then once you are sunk, that friction comes really strong, it returns really strongly. And this can be a really, really, really big pain and potentially dangerous. Getting out is possible. Depending on the situation, it might just be a pain. You'll get pretty muddy. You might have to sit down or hold on to something, or like Sunny said, maybe somebody offers you a branch for stability from the side, and that's important. So that what that does is it allows you to move and wriggle the foot or whatever is trapped. And what that does is it decreases that solid stability and it allows water back in, which lessens the friction. It kind of like it creates tiny spaces and pockets for water to come in from the side. That replaces really what was a vacuum, and the compactness of the quicksand around your foot. That water starts to release the pressure, and then you should be able to wriggle your foot out. Again, it was that downward pressure that got you stuck. And so now you're trying to kind of break up that, creating spaces and getting your foot out. And so pretty much in any scenario, you should be able to do that. And it's similar to using a suction cup. When you release the air between the cup and the object, it forms a vacuum, and all of the pressure then, all of that air pressure is holding those two objects together, basically the suction cup and the object. And to release that pressure, you need to introduce air into that space. And that's so, again, this is water instead of air in the case of quicksand or mud, but it's a similar object. You want to keep that pressure, you want to break that up and decrease the friction. So if you have the time and patience, and we'll watch a video after this of Bear Grylls, and I'll share the link for those that aren't watching it live. You should be able to get out of any quicksand situation. However, it will take time, and time and panicking are not your friend. But just thinking of time, you could be in a mud flat in a tidal area, and all of a sudden that tide is coming in. So now it increases your anxiety, it increases the pressure, and getting out does take time. So you might not have the time or the patience or just the wherewithal to remove yourself as you start to panic, and a tide could come in that time, and depending on how deep that tide is, it could kill you. Or let's say you're stuck and you're exposed to the elements and this like the sun or something else that, could be really deadly, if you're pretty badly stuck and you need that time, you can't move and you're exposed to any dangers in the environment. So desert oases can be really dangerous with that really hot sun if you do get stuck in quicksand there. And people do die from these unfortunate events. But the movies, of course, taught us that when you're stuck in quicksand, you get somebody else, you call for somebody else to help, right? And they're going to pass you a stick, or they're going to give you their hand, or they're going to give you a vine, so they can pull you out. So not only is this dangerous because now you're calling somebody else who can also get stuck, but physics tells us that it is nearly impossible to just pull your foot out. If you got a shoe and you can pull your foot out, that's super helpful. But if you can't get your shoe off or you don't have a shoe, pulling your foot straight out is nearly impossible. In fact, it takes about the same pressure to pull a foot out of mud or quicksand as it would require to lift a medium-sized car. That's how hard it is to just pull against that pressure without doing the wriggling. And so in the movies, somebody gives them a vine and pulls them out, but really that would be you probably couldn't, and if you pulled hard enough, you might just, basically rip that person in half or something more gruesome like that. So it's similar to getting out of water, even in regular old water. It obviously different properties, but what makes you sink is if you can't swim, or even if you can, it's the constant thrashing from the anxiety and from the oh crap, that thrashing actually pulls you down in the water more. It's similar in mud. If you can get yourself stuck in mud and quicksand, and you can push yourself deeper with that movement, and it just makes the problem worse. So if you do find yourself in a bad situation, the the recommended course of action is, first of all, to remember you're not going to sink, and hopefully you have time. If you're deep enough, you want to get in a supine position on your back. If you're by yourself and you can't get your foot out, you would, basically lie down or sit. And again, parts of you would sink. But then if you get yourself in that position, you can start to wriggle your way out and keep yourself flat. Probably similar to, if you fall in ice, you want to kind of keep your distribution. But it's really that recognition you're not going to die, you're not going to sink, and then you can start to work out whatever's stuck, and you will be fine, remaining calm and understanding you won't drown. And that is super easy for me to say from my comfortable chair in my office because I'm not actually stuck in quicksand. So, but it's kind of like, if you're being stalked by a bear, like what you're supposed to do is make yourself big and scare the bear back. The question is, will you remember to do that, or will you think about doing that when you're in that actual situation? So one of the really cool things about quicksand and those who study is that they're embarking in a field of study called rheology, and that's the study of how matter deforms and flows, and often focuses on the unusual things like mayonnaise. And Josh and Chuck talk about how it's technically liquid mayonnaise, but what liquid do you know that's going to hold its shape after you take a knife and move it around, right? That liquid shouldn't do that, but mayonnaise does. So it studies things like silly putty and foam and the non-Newtonian liquids like cornstarch and water. Not everything fits nicely into that solid and liquid box. There are all kinds of unusual substances that are more complex, and quicksand is one of them. The Greek word rheos means to flow, and so this field is studying the things that flow. So it can help manufacturers or, builders predict if paint's gonna drip off a wall or stay stuck, or if a topical pharmaceutical, is it gonna spread on your skin or is it gonna clump? It's a super interesting field of study, often used in the culinary arts, but basically how things flow and really focuses on the atypical liquids. So many things are liquid that we don't really think of as liquids. And before we go, you may have heard of something called dry quicksand. Dry quicksand isn't technically quicksand because there's no water, and for quicksand you really need the water component for it to work. But dry quicksand is sand that is so loose that it can barely hold its own weight. So by itself it's going to be stable, but any disturbance, like you walking on it, would make it so unstable that those properties that make it a liquid would instantly swallow you up. So it'd be more like the earthquake-induced quicksand or sinkhole, but in this case, it's sand and no without that water to create that buoyancy. If you stepped on it, you would poof, you would just disappear. Probably similar to I'm thinking, and probably is similar to, if you're in a people die in silos of grain where there's just it's more like that. Dry quicksand has been created in labs, but does not exist in nature that we know of. So in theory, you can produce it, and this is an example of it in a in a swimming pool here. But if it were to exist in nature, it probably the most likely cause would be if sand were kicked up in a dust storm, sand gets in the atmosphere, and then it gets deposited in such a loose form. In theory, that could be deadly, but there is no evidence that dry quicksand exists in any natural state as of yet. If you want to ignore everything I said about how quicksand works, you can go ahead and go back to what the movies tell you. You can even go to a website called quicksandsmovie.net for a list of all the movies and TV shows that have people sinking in quicksand. If you care, Gilligan's Island leads the pack with 5 quicksand episodes. And General Hospital and Fantasy Island have 4 episodes. Again, these are mostly older. You got Dynasty, G.I. Joe, Benny Hill. The Simpsons have 3 episodes. Magnum PI, MacGyver, and they often have it's usually on islands. It's usually on tropical islands. Again, that's probably why Gilligan's Island that usually you find the quicksand. And you know, Princess Bride for the younger generations, Indiana Jones, Blazing Saddles. But this meme is so true because at least for me, I saw the movies, I saw how dangerous quicksand was. I started to prepare myself for that inevitable time when I would be in a forest or a jungle and I would take a step on what I thought was solid ground but wasn't. And then I'd have like 2 minutes to try to save myself before I finally sunk slowly beneath the surface with just my hand above the surface before I disappeared forever. So if you don't want to let science rain on that parade, you believe what you want to. I'll probably still believe in it a little bit. But that's quicksand. And thank you for joining us. I will stop sharing my screen.